let's look at a few ways to prepare metal alkyls or synthesize them. So going back to some of our first examples of prepared metal alkyls, let's look at how to make that tungsten hexamethyl complex. So one of the ways that we could use is by using a very nucleophilic carbon. So we have our tungsten, and we can just start with the chloride of this complex, and then we'll add an organolithium reagent, which is a very strong nucleophilic reagent. So it will want to attack this positively charged metal and substitute for the chlorides. So we'll do the typical organic chemistry synthetic reaction scheme, and we'll just say, let's add this organolithium reagent into the mixture. And naturally it will take 6 of these, and we will make the tungsten with the metal alkyl. With 6 methyl groups, plus we'll make some lithium chloride. So that's one way. And another good reagent to use for these is not just the lithium reagents, but you could also use organozinc reagents. So a very similar scheme would be starting with some other metal chloride and adding the organozinc. Reagent. Either one of these can sometimes be used to change out what is on the metal. So this is a nucleophilic attack. So in order to do that, we'll have to have conditions that would allow for these reagents in there. So just keep that in mind. It's also possible to instead of using nucleophilic attack, we could use electrophilic attacks. So if we start off with negatively charged complex, and later on we can talk about stability of complexes, but one of the ways to stabilize a metal complex in a very low oxidation state is to put a lot of carbon monoxide ligands around it. That tends to stabilize it in a low oxidation state. Often you'll see these metals as either 0 oxidation state, or in this case we have a negative charge there. So then if we add an electropositive carbon, such as the halide, so we'll use methyl iodide here, then we can add a methyl group onto the manganese. In an electrophilic fashion. Now, one that you're probably familiar with but might not know the name is oxidative addition. So oxidative addition is going to, well, it's going to oxidize the metal, and it's going to add some ligands to the metal, hence the name, oxidative addition. And Grignards are a prime example of oxidative addition being used to synthesize a metal alkyl. So we start off with a metal in the 0 oxidation state, and then we add some metal alkyl. Let's use butyl bromide. And then we're going to oxidatively add, so the metal is going to insert itself in between these two groups, and the charge on the metal is going to increase by 2, and the electron count was also going to increase due to the addition of these ligands. So you'll notice that the charge on the metal has increased by 2 units. So this is now Mg2+, when we started off with magnesium 0. So this is oxidative addition. Let's look at another example of oxidative addition using iridium. So here's an iridium complex. It's got some other ligands on it. And then we're going to add our methyl iodide in. And then that is going to oxidatively add to the metal. So we will end up with our methyl group on the metal. We'll write it right here first to emphasize that it's there. And then we still have our other ligands. And now in oxidative addition, we're going to add both of these species to the metal. So we're going to have our iodide on there as well, and then our 2 ligands that were there before. So that's another way to do it. And surprisingly enough, in some cases, we can actually go backwards from a beta hydride elimination to actually make a metal alkyl. It's possible to go both directions in some cases. So here's how that scheme works. And this is called insertion. In fact, it's 1,2 insertion. And 1,2 insertion is the opposite of beta hydride elimination in this case. So 1,2 insertion would look like this. We have our ligands, we have our metal, and we'll have to have a hydrogen. We'll have to have a metal hydride to start with, and then we'll need to add an alkene. So I'll just use the simple alkene here of ethene, and then we take that, which I guess I've written fairly lightly on there. And what this will do is the reverse of the beta hydride elimination, and we'll end up with this. So now we have an ethyl group on there because this has inserted itself in between. I'll make that a little bit bolder. The ethene has inserted itself in between the metal and hydrogen bond. And so, say this first carbon has bound to the metal, and that hydrogen will end up on the second carbon over here. So those are some of the ways that we can synthesize metal alkyls. There are, of course, more, and there are more examples, but these are some of the basic ones to get us started.